Okay, so you should have already watched the YouTube video that talks about the Boltzman distribution and how activation energy plays into kinetics. And if we go back to first year chemistry, we briefly touched on collision theory, and we talked about what it meant to have a successful collision just in very basic terms. So we said that the molecules must collide with one another, that they have to collide with what's called the correct orientation. And we didn't get into much detail about what that meant. And we'll actually kind of circle back to that and talk about, well, what does it mean to have the proper orientation to react? And then the last part of the collision theory was that the molecules must have enough kinetic energy to break and reform bonds. And so that we talked about as our activation energy. So when we talk more about these successful collisions, we know that if two molecules collide and it's not the correct orientation, that their collision is said to be ineffective, and so we won't get a reaction. They've got to have enough energy when they do collide with one another so that they can lead to a reaction. And we know that at really low temperatures, if we think about those molecules being kind of sluggish and that they're not colliding with one another, that it's very difficult to have this successful collision. So at higher temperatures, there's an increase in the number of effective collisions. So kind of the gist of this is that reaction rates increase when you're at a higher temperature. Now, something that can confuse students is, well, we've talked about Le Chatelier shifts, and we've looked at, well, if temperature is high, for an exothermic reaction that's reversible, that would actually shift the reaction to the left to favor the formation of more reactants. That is still true when we're dealing with equilibrium systems. But in general, if the temperature goes up, the reaction rate goes up. And we know if we have a system that's at equilibrium, then that means both the forward and the reverse reaction increase, if that makes sense. Sometimes that's difficult for students because they're so in the mindset of Le Chatelier, but anytime you increase the temperature, you will increase the reaction rate. In our thermo unit, we looked at energy diagrams like this one, and we talked about the fact that reactants are always over here on the left-hand side, products are always going to be over here on the right-hand side, and that activation energy is always measured from the reactants to the peak. So if I wanted to measure activation energy, there it is, right? Now, they've shown this decreased hump, and that would be the energy diagram for the catalyzed. And notice they've shown this over here. This is for a catalyzed reaction. So really what a catalyst does, because it's not participating in the reaction as far as a reactant or a product, it provides this alternate pathway, and a lot of times it has to do with surface area. So it's increasing the surface area in which the reaction can take place. And so that actually lowers the activation energy. So the hump is smaller, so the reaction happens faster. So make sure that you're still comfortable reading energy diagrams and that you understand, catalyzed versus if I added an inhibitor, right, that would actually increase. Preservatives in our food are common inhibitors, right, because they're trying to slow down the rate of reaction for things like mold and bacterial growth. So low activation energy means that it's pretty easy for the reaction to take place. A high activation energy means that it's going to be difficult, that you've got to have enough collisions and you've got to have the right amount of energy. So we talk about the activated complex. Again, in first year, we just kind of glossed over it. We said, oh, we've got this activated complex up here at the top of the curve. Well, that's where, it's represented based on that. But what does that mean? And if you think about the roller coaster example, right, it's like you're at the top of the hill, you've got almost enough energy, and that potential energy is about to be converted into kinetic energy. So we've got what are called these intermediates, and we saw these when we talked about reaction mechanisms. Those are things that are formed by an elementary step and then consumed in subsequent steps. So even though we've gotten very used to talking about, reactants form products, and we have this single reaction, we saw that in reaction mechanisms, a lot of reactions occur from multi-part steps. And so we can actually have these intermediates that are formed and then used up in subsequent steps. So for the first practice, we're just looking at this energy diagram and labeling the different parts. So it says the chemical composition represented by Q star is an activated form of, well, here are our reactants and here are our products. And so this Q represents an activated form of the reactant. So it's an activated form of the N2O5. It asks about line segment A. Well, line segment A is measured from the products to the peak. So that is not activation energy. That is actually the activation energy if the reaction were going this way, right? So we would say this is EA for the reverse reaction. Line segment B, this one, is, you'll notice, measured from the reactants to the products. So it's the difference between reactants and products. And so that is delta H. That is the change in enthalpy for the reaction. And if we look, right, this can't magically happen. We can't increase in energy magically. So what had to happen? Energy had to come into the system. And so this is an endothermic reaction, and our delta H would be positive here. Line segment C is measured from the reactants to the peak. So that is our activation energy for the forward reaction. And then it says if this reaction were catalyzed, the effect would be 2. Well, that's going to lower the peak, right? So now Q star would be somewhere in here. And so our peak would be lower. So the things that will change are anything that involve that peak. So A would be a smaller value, right? C would be a smaller value. And would it change anything about B? I think we had this on a previous test when we were doing thermo. B doesn't change. So adding that catalyst doesn't change anything about the energy of the reactants or the products. All it changes is the hump. And so we would have changes in A and C, and they would be lower. But our delta H would not change. So the screencast that you watched earlier, I just thought he was really eloquent with how he explained the Boltzman distribution of energies. College Board loves putting these graphs, on the AP exam. And so if you think about, the little particles under this curve, right? What they're trying to represent is the particles that potentially have enough energy for the reaction to take place. And so, he kind of marked this spot, EA, and what happens as you increase the temperature for the probability of having successful collisions. So, what I like about this picture, and this is in color, so it'll probably help you on your notes. Notice they've got these different temperature ranges, right? And what stays constant is the area under the curve. So if you came in and measured the area under this curve, these 3 curves that they've given you, it would remain the same. But what you notice is this shift, and it's a shift to the right. And so it's kind of a smushing and a shifting to the right. And yes, smushing is the technical term there. Pushing it to the right so that now, if this was our activation energy, you'll notice that you got more particles. So this blue represents the portion of particles that have enough kinetic energy for the reaction to take place. That's at 0 degrees Celsius. It's pretty chilly, and there's not a lot of particles at that temperature that would have enough activation energy to react. So then at 25, you notice the curve kind of comes and spreads out this way. So now all of these particles, right, the blue and the green. So notice you're increasing the number of particles that have enough kinetic energy for a successful collision. And then the last one at 100 degrees Celsius, again, we've smushed and we've shifted right. And so now we've got all these particles that now have enough energy for the reaction to take place. And so this is key. The total area under the curve remains constant. So when we come into class, we're going to talk about what's called the Arrhenius equation. And if you remember, you've seen Arrhenius' name before. He had, an acid-base theory named after him. He also did some studies with kinetics. And so we're going to use this equation in class to kind of bring all these factors together. So you have collision frequency, which gets this Z term, and so that's basically just how often are they colliding with each other. And then you've got this steric factor P, And these, I don't want you stressing a whole lot about these because these are actually absorbed into this one factor, which is called the Arrhenius factor, the frequency factor. So it also takes into account, the fraction of particles that have enough energy to produce the reaction. So it kind of puts those two things together. And so it combines it with this A term, okay? And it's a combination of collision frequency and what's called the steric factor. So you'll notice in the equation we've got our activation energy, we've got an R, and we've got a T. And so we've got our Kelvin temperature, of course, and then remember, anytime you're using energy, you're going to want to use that 8.314, not a 0.0821. So that's our energy term, and watch out because that's in joules. So your activation energy better be in joules as well, or this thing better get converted to kilojoules. So this, really, you don't see that form very often of the equation, and again, I kind of glossed over it, but there's your K, there's your rate constant that we've been working with. This is the more common form that you see, and again, you notice, hopefully, that it's in y equals mx plus b form. And so typically this will be given to you graphically. So they may give you a graph and tell you what the slope is, and you may be wondering, well, why have they given me a slope? Well, they've given you a slope because what can you find from it? You can find the activation energy because R is just a constant. So if you plot the natural log of your rate constant versus 1 over temperature, so that's your x, then you can get the slope of the line, and that will help you get your activation energy. So that's what we'll do in these problems when you come back to class, and we'll practice those together. So make sure you understand, the different parts of the equation, and then we'll pick up from there and do some practice.